So we will start. Let me invite you all and thank you for joining the last speaker session for today. And thank you for coming. And just a small introduction, we started already to present Professor Täuber. Maybe people like Yuri Vasilievich, Rainer Fold may said much more, and you will represent yourself also much better. But just let me tell a few words to announce today's speaker. So Professor Täuber, he sorry. He received his PhD from the Technical University in Munich in 1992, and then did the postdoctoral research at Harvard University and Oxford University. And later he joined the Faculty of Physics department at Virginia Tech, and proceed working here till now. He was inaugurated as director of Virginia Tech Center for Soft Matter and Biological Physics from 2016 to 2022. And also he was elected like the lead editor of Physical Review E. And his research interest he will present today, but mainly it's about theoretical condensed matter and statistical physics of complex non-equilibrium systems with a lot range of applications from material science to ecology and epidemiology. So today talks is about stochastical spatial Lotka-Volterra predator-prey models. So please start your interesting lecture, and we will pay attention, and people who want to ask the questions, either ask the questions or raise your hand, and I will interrupt the speaker. So thank you, and please proceed.
Wonderful, Mariana. Thank you so much for this kind introduction and the invitation. It's not just a pleasure, but an honor to be giving one of these Ising lectures this year in really difficult times, obviously for you in the Ukraine. Needless to say, let me emphasize that really the Ukrainian people are not alone. We are certainly heavy in our thoughts and wishes all the time. We often wish we could do more to help you in these, awful time period, and hope it will soon pass. Before I get started with the science, let me just say, if we can help, as I said, we feel helpless a lot of time, but if we can help, please do let us know. You all have a lot of friends in the world, and try to use that. But at least you're in our thoughts, and as I said, it's my pleasure and honor to be delivering this lecture today. So I'll be talking about stochastic spatial Lotka-Volterra predator-prey models, which of course I will explain. This is an application which I think is quite cute on statistical physics methods in ecology or biology and these kind of systems, of which we heard quite a few things already during this series. And I'll get to that later. We started this somewhere around 2005 or 6 with initially a very talented group of postdocs, Mauro Mobilia, who's now at the University of Leeds as a senior lecturer, and we're actually still collaborating, and Ivan Georgiev, who did the initial set of movies I'm going to show you, and then went off to make money. And then a talented undergraduate, Mark Waschenberger, who also is in industry now, and a set of graduate students, among them Xian He, Ulrich Dobramüsel, now at Oxford, Sheng Chen, and more recently Shannon Zarao, an undergraduate Lazarus Arnau, and current Mohamed Swalem. We got support for this initially by the US National Science Foundation, and lately again, initially from materials research, lately from the Division of Mathematical Biology, and also in between from the US Department of Energy, and intriguingly, the US Army Research Office. All right, after having taken care of these necessary introductions, I'd like to tell you what I'm going to do. I'm going to define what I'm going to be talking about naturally. And we're looking at some kind of interesting noise-induced spontaneous structure formation, and then correlation effects there. And then once we're done with this, I'm going to look into some aspects that are kind of more physics-informed initially, such as phase transitions and resonance effects by external driving. And then asking some questions on the system that are kind of more biologically motivated, such as about environmental variability, demographic variability, and then also some extensions. But as Mariana just said, please, if there are any questions in between, do never hesitate to interrupt. I don't need to get through everything I have here. I'd like to get started with this kind of, philosophical and almost ideological brief introduction, which nicely ties back to some things that Caroline said in her first Ising lecture 2 days ago. And this is how can you use tools from statistical physics generally outside traditionally its field. Now, it's really traditionally its field. Statistical physics has branched out quite tremendously, and that's why it's so fun to work with. And let me just get maybe to the second itemized point here first. If you look into biological systems, which is some of the systems we have been investigating in the past, as I said, 15 years or so, in biology, you almost by definition deal with complex, cooperative, and definitely non-equilibrium phenomena. You often have non-random structures. They're functionally optimized, something that we just heard nicely about in the previous presentation, and I won't touch much upon. But definitely these are not uncorrelated independent systems. Correlations are crucial. They're especially crucial in the dynamics. And, they show up on the very basic levels, such as diffusion-limited reactions, which, however, are the same language that you would use to describe population dynamics, ecology, and, infectious spreading just as well. There's often history dependence, there's evolution, and there's feedback. And spatial fluctuations, most decidedly, are non-negligible in biological systems, and simply because they're actually quite prominent already just in non-equilibrium steady state. And there is a lot of fun with transient features. So one caveat I need to make generally when we come, say from traditional solid state or condensed matter physics, if you look into biology, systems are a lot more finite. They're certainly sufficiently large that you can apply statistical tools, but you're not typically talking about 10 to the 23 degrees of freedom, but maybe 1 million or 1,000. And so you have to worry about finite number fluctuations, finite size fluctuations. The thermodynamic limit need not quite apply, and life is transient. So temporal transients are absolutely crucial. Now, what I'm going to do, as opposed to Nier's very nice talk, who actually talked about real animals and brains, I'm going to do the typical physics approach, very much in Heisenberg and Lenz in Ising's venue, to look at simplified, very paradigmatic model systems, but try to really fully understand and characterize them. And then maybe take these kind of spherical cows and put them back together again to get to something more realistic. So that's my ideology slide. With this, I can go forward and actually define the model we're going to be looking at with various variations. This is a very classic, 100 years old now, model for predator-prey competition, or, actually chemical reactions that was written down independently by Lotka and Volterra. The way I would like to describe that today is using a language of population dynamics and ecology, but a description level that looks like chemistry. So we're taking two population species. One I call predators and one I call prey. The color coding throughout will be the predators are red and the prey blue. This is not driven by recent events. This we invented already in 2005. But never mind, the predators by themselves die out. So they have a finite death rate that I'm going to call mu. The prey by themselves spontaneously produce offspring through this kind of asexual branching or reproduction process with a birth rate sigma. So these are probabilities per unit time. And so left by themselves, the predators will go extinct and the prey will just fill the entire system and undergo Malthusian population explosions. And so the interesting dynamics here happens once we allow for a nonlinear reaction between those, which are called predation. And that is when a predator particle meets a prey species member, the predator will do its job and devour the prey. So the prey will be disappearing. And since the predator just had a really nice lunch, they're happy to reproduce. So in this very same step with a unified, just overall rate that I call predation rate lambda, we're just essentially replacing upon encounter a prey individual by a predator individual. And so that is the simple model we're going to look at. And of course, you can ask a lot of questions about how realistic this is and what you like. So as we would now say, what Lotka and Volterra wrote down 100 years ago is really a mean field type of rate equation for this. And so this comes with approximation, which is the usual mass action factorization for correlation functions. More precisely, if I look at the predated particle number or predated density, of course they undergo this radioactive decay with rate mu owing to their death processes. Likewise, the prey have this exponential increase with rate sigma. But here's the competition part, which is the nonlinear process. And what I really should have on that right-hand side here is some two-point correlation function. That is a measure of the joint probability of particles A and B occupying the same space-time point at any given time and space. And so what we're assuming here is that we somehow think we have a well-mixed system, there is no spatial structure, and we're also ignoring temporal correlations, and then just factorize this two-point function in a product of concentrations. This is what everyone in mathematical biology and in physical chemistry tends to be doing, but it is a brute approximation. It's a mean field approximation that ignores correlations and fluctuations. When we do this, we transform this equation into a nonlinear set of differential equations, coupled differential equations. At this point, no spatial dependence yet. And then we can, of course, analyze that. And so following Lotka and Volterra, what you do is you look for stationary states. Well, obviously, everyone is gone. That's complete extinction is one stationary state. The other stationary state is all the prey are gone. And then, all the predators are gone, in which case the prey explode exponentially. So that's the decoupled state. Both of these are unstable linearly. And there is a coexistence state. So I can just find that by, let's say, looking at the second. Let's look at the first equation first. So we're looking at the stationarity for the predators. And you see that this enforces the prey density to be the ratio of this predator birth rate and the predation rate. So, of course, the prey like the predators to die fast. And they also like the predators to be not efficient in devouring them. So this one is very intuitive. But if you look at the second equation, which gives us the stationary density for the predators, that is less intuitive. It's obvious that the predators like a lot of food, so they like the prey to proliferate fast. But the stationary density for the predators is inversely proportional to the predation rates. So it's not actually too good for them to be too efficient because they're just eating their prey too fast. But it turns out in this differential equation system, this stationary point is actually never realized. What happens is there is a conserved quantity on this mean field level and only there, which happens to be this combination of densities and logs. That is just time independent. And that immediately implies you need to have nonlinear oscillations that take the system precisely back to its initial point. So this is kind of shown here in a phase space plot of prey versus predator density, and down here in the time-resolved trajectories, which are the famous Lotka-Volterra oscillations. So the system doesn't actually find this kind of central stationary point, but just oscillates around it. That is not realistic in any sense ecologically, or biologically, or physically for any complex system like that. So that's clearly an artifact. And what you can, of course, also do is you can investigate these kind of oscillations in the harmonic limit. So, small deviations from the stationary point. So we're kind of here. And naturally, this becomes circular. So, of course, you get kind of, linear harmonic oscillations there. And if you do the linear stability analysis, you find that the oscillation frequency in this linear limit is just the square root of the predator death and the prey birth rate. So that's the classic picture. Now, as I already said, there's clearly some fine-tuning here that prevents some kind of exponential, which is what you would expect, relaxation into the stationary point. You get these neutral cycles as a consequence of this conservation law. But that is a mean field artifact, really just doesn't happen when you don't do this factorization. And is also consequently very susceptible to small model changes. So this is not robust. And if you have a non-robust description of a physical or biological system, you really don't want to believe it. So one example for modifying this is slightly and making this more realistic is you're putting in what is called a carrying capacity. And let's just do that for the prey. So as I said before, when the predators would die out, the prey would proliferate exponentially. And that doesn't work, so we need to cap that somewhere. And one way to cap it is give the prey density a total maximum density of 1. For example, generally there's some carrying capacity rho. So we just modify first on this mean field level the prey evolution equation by this 1 minus density term, which limits the total density to 1 and makes the prey equation of motion look a little more like a logistical kind of equation that you might be familiar with. Now, very interestingly, that immediately induces a extinction transition. And so we are messing with the proliferation of the prey, but that induces an extinction transition for the predators. And so if there isn't just enough food and the predators are not really great and effective in their predation, they will die out and the prey will just take over. That is what is called, once you allow for stochastic fluctuations, again, an inactive and absorbing state, because once the predators are gone, they cannot come back, and we are just stuck in this state. As before, without this restriction, there is an active phase of coexistence of predators and prey, but it now has kind of two sub-phases. One is that there's no neutral cycles anymore, but in one case you get a direct exponential relaxation to this stable fixed point, and in the other situation you have oscillations, so you get kind of spiraling back into this fixed point. And these two phases are separated by, on this mean field level, a bifurcation transition that is continuous. Back in a fully spatial system, a genuine non-equilibrium continuous phase transition from an active to an absorbing state, which generally you would expect to be in a certain universality class that I'm going to be talking about. So to really treat this, we are going back onto the lattice and doing stochastic simulations and then some more things with it. So we're leaving this mean field description. We're most definitely leaving this factorization approximation and generally taking into account fluctuations and correlations. So how do you do this? You take your particles A and B, throw them on a lattice. Simplest situation, we have a single particle per site, so we have full site occupation restrictions. Then you pick a particle, it checks their neighbors for free sites so it can proliferate, or it checks them for, if they're predators, it checks them for prey so they can eat them. And then you just take these stochastic reactions as a Markovian Monte Carlo stochastic process, loop it, do periodic boundary conditions, and see what happens. So in a phase-based plot, this is what happens. We now have the total density A plus B limited to 1, so we're really only in the kind of lower triangle on this phase-based plot. And you see for small predation rates, keeping everything else fixed, you run into this absorbing state. So the predators, the system reaches this border, the predators will go to 0, and the prey will just take over to density 1. Then there is this now genuine continuous phase transition, above which we have coexistence at finite densities for the predators and prey. Near the transition, we get a direct exponential relaxation toward the stationary point. And further down, we find this an analog of the kind of mean field focus behavior with spiraling trajectories. Here's one example, and a more prominent one in this black trajectory here, which happily spirals into this point. But it turns out it's not actually spiraling into this point. There is fairly large fluctuations in here. So we are noticing something that I'm going to show you in some movies next, is that we get sharp stationary points here, and they become a lot more diffuse for larger predation rates. So as I'm actually going away from this non-equilibrium phase transitions, we get an enhancement of fluctuations, which is odd, but there you are in the non-equilibrium world. Now, one caveat I should make before showing some simulations: this is a finite system. We have an absorbing state. So of course, the only stationary state, mathematically in a finite system with an absorbing state, is that absorbing state. So ultimately everything will just go extinct. That's a true statement, a true and useless statement, because it never happens in a realistic setting. And that's because the corresponding extinction time grows exponentially with the number of lattice sites or individuals. So it becomes really huge. And we never see that once we go to something like 10,000 lattice sites or something like that. So beware of exact mathematical statements if you want to say something useful already in condensed matter systems, but definitely in biology, where these transients are the most important bit. Okay, let me switch to the next slide, but also pause and ask the audience if there are any questions so far. Is the model clearly defined, the setup we're playing with, and can I proceed? Are there any questions on the chat?
No questions and no
No
raising.
questions? Excellent. So I'm assuming this is all crystal clear. If not, it's your fault because you should interrupt me. All right, so I'm going to show you a first video which is close to this extinction threshold, but beyond it. So roughly this kind of parameter regime, where in the mean field approximation, you would have a nodal fixed point. So direct exponential relaxation, and indeed things will go fast. This is a 2x2 lattice. Red particles are predators, blue are prey, and not possibly too visible are black things that are empty. And we run this, and as we run it very quickly, we run into this stationary state, non-equilibrium stationary state, essentially a sea of blue, that's the prey, that almost fill the system, except for some, clusters of predators that eat their neighbors and leave behind some empty sites that are then filled by the prey again. And so that's it. Not too exciting. That's simple small clusters, small typical length scales. And if you watch this, you might see there's a drift to the right. The origin of that is that Ivan, when he wrote that simulation 15 years ago, got so bored that he only let the predators eat their right-hand neighbors. And we wanted to see if that kind of additional drift term makes any difference, and it doesn't. But that is what we just saw. So this is maybe the simplest scenario that you would expect and pertains to this kind of focal mean field regime. Now this one is now for really large predation rates. So
I'm sorry.
Absolutely, please.
You said it's very important that you have finite systems, and now you show very precise curves. How do these curves depend on the size of the system you consider in your simulation?
If you give me a second, Reinhard, I'll come back to that. But what I showed you, these are actually all single trajectories. We'll later show averages. The short answer is, once you're big enough, and that of course depends on things, it really doesn't matter so much anymore. And the actual extinction is really excluded by any finite time we can run it. Finite time not just being the lifetime of a graduate student or myself, but essentially the universe. So in the simulations of these lattice sizes that I'm showing you, there's never extinction. Just doesn't happen.
Thank you.
So, more technically, the usual thing applies in phase transitions. You need to do first the thermodynamic limit and then change parameters. So in our situation, we need to do that too and send time to infinity first. But in these finite systems, that limit is kind of done automatically. The times you're looking at are always sufficiently big that we're not running into any issues. But that's something always to worry about. Okay, so let me go back to this large predation rate limit. And so same setup, same initial density, about 40% prey and predators. That'll be completely forgotten, and the system does its own thing. Predators are very effective in eating, so they will devour almost all the prey. And we see this very clearly here, it's almost red. Then the only thing they can do is die. And so the system almost goes black or empty. But there were a few survivors of prey that then spread happily into the empty region by these blue fronts. And of course, they're followed by a few happy predators that were still around and now have food, leave behind some empty space that's followed by prey expanding and predators following them, otherwise dying and so on. And so you get these concentric activity fronts that at some point, of course, and owing to periodic boundary conditions, will interact and talk to each other. And the system will just do what I'm showing you. And that is the stationary state, certainly in these finite systems, and we'll just keep doing this. And so we get these fronts of a typical size that would just continue throughout the system. And that was a really, nice and beautiful surprise we had initially. And what that means is that locally and globally, you get population oscillations, right? And so here is one of these tracks that gives you this big blob in the center and shows you, because of these fronts that keep moving through the system, you keep exciting the system and you never quite reach a completely boring stationary steady state, but it always has this kind of spatio-temporal structures. If we forget space again, but keep time and do worry about temporal correlations, McCain and Newman, also in 2005, analyzed the system. And if you want to kind of hear in a nutshell what's really going on is, it is an oscillating system, right, as I showed you before, nonlinear oscillators, but you essentially drive it with internal reaction noise. So internal, almost white noise, And if you drive an oscillator with white noise, you're going to hit the resonance frequency inevitably at some point. So when you hit the resonance frequency, you're spiraling in trajectory. It's a damped oscillator. Your spiraling trajectory will be pushed out again, spiral back in, being pushed out again, spiral back in, being pushed out again, spiraling back in. And that kind of resonant amplification of stochastic fluctuations keeps the system going in a zero-dimensional case. And in a spatial system, it's really these persistent spatio-temporal structures. So let me show you one more and then get to Reinhard's question. This is in between the scenarios we had before. So we are still in the focal regime, if you like, on the mean field level. So we do have oscillations, but we're closer to extinction. So there's a lot more blue than there's red. And now the activity fronts of predators moving to the system look a bit more like, you know, what you see in forest fire models, right? So these are fronts that devour everything in their wake and then get rekindled somewhere else and then go again. So Reinhard, here we go. These are actually down here. This is these oscillations now tracked over the entire system and averaged over realizations for different system sizes. So the black ones is 32 squared, red is 128 squared, and 512 squared. And you see, of course, the oscillation amplitude goes down. And that's because these oscillation amplitudes are averaged over the entire, and you see there's stochastic fluctuations on these. The oscillation amplitude goes down because what you see here is kind of, you know, independent oscillators at various places in space. And the larger I make my system, the more of these independent oscillators I have, because they all have the same characteristic front scale. And so I'm just averaging over more and more out of phase oscillators, and that will, after averaging, take down the amplitude of these fluctuations. If I look locally, things are just oscillating like crazy. So I hope that answered part of your question about finite size effects. So yes, this is a finite size effect. If I go to infinite system and average over everything, things will go away. But I keep averaging locally, I will see very strong oscillations. All right? So that is, you know, the nice pictures. Of course, you can do a quantitative analysis of that, which we did with, you know, first with this undergraduate student, Mark Boschenberger. And the first thing to see is, you know, if I now run these stochastic simulations, these are predator and prey oscillations. This one happens to be simulations where we did not have side restrictions. We're really just interested in these fronts in the active phase. So we took away with the transition. And we also, just for the fun of it, plotted this supposedly conserved quantity k of t that I showed you, which is this kind of first integral of the mean field rate equations. And there's nothing conserved about it. And so it's really a mean field artifact. And, you know, let me just generally give you the warning here that you want to be really aware that there are real conservation laws for these kind of stochastic processes that are physics grounded. And there are fake conservation laws that just come up in certain approximations and can give you all kinds of spurious results. So beware of them and avoid them. Anyway, we can now do a Fourier transform of that. And with the Fourier transform, which is shown here in red and blue, you know, somewhat noisy data, of course, you can look at the peak position, which gives you characteristic oscillation frequency, and you can look at the width, which gives you damping coefficients. And so you can extract quantitative information. And you can also look at correlation functions. So this is the predator correlation function plotted on a linear log scale, because we expected some exponential behavior, which we're roughly seeing. So from the slope here, you can extract some correlation length. But anyway, you see that typically things decay on the scale of maybe 20 lattice sites or so. That's just the front width of these activity fronts we were observing before, so not too surprising. And then you can also look at predator-prey cross-correlations. That also behaves precisely as it should. So this is just a mathematical sanity check for all the things we were seeing. At low distances, you get an anti-correlation. This is negative because it's really bad news for the prey to come too close to the predators. So this is what you're seeing in this corner. And then around, you know, 6 lattice sites or so here, you see the positive correlations. That's really the prey front being ahead of the predator front by that distance. But correlations are short range, right? It's nothing that spans the entire system, no critical behavior here. Nevertheless, they're really strong renormalizations. So the mean field prediction, certainly of the linear regime of the oscillation frequency, is massively off. And so that's kind of shown here. The dotted line would be the square root of mu times sigma. So that's the predator death and the prey birth rate. And in a log-log plot, that's a straight line with slope 1/2, which is this one. And then we extract it from these peaks, the characteristic oscillation frequency is function in mu and is function of sigma. And, it roughly follows that square root behavior with some deviations out here, but an offset that is about a factor of 5. So the actual frequency of oscillations that we see is off by a factor of 5, not 5%, but 5 from the mean field prediction. So we have strong minimalizations due to these internal reaction noise and spatial correlations. You can try to figure out why that is. For that, you do something that I really don't want to talk about today because it's quite technical, but a lot of fun. And I know there's a lot of people in this call who are sharing my passion for doing these kind of things. You can take these stochastic processes, actually map them onto a stochastic field theory, which is a dynamical field theory, and then you can employ the standard tools of statistical and quantum field theory, like writing Feynman diagrams, doing perturbation theory, and the like, and do a first-order correction analysis, so one-loop analysis, and you find there is indeed a strong minimalization for the frequencies and other things. So we have a qualitative, at least, perturbative understanding of why that happens, but it's quite intriguing. All right. With this, maybe let me spend 5 minutes or so to address the extinction point of the predator. So once again, we let the prey be subject to, say, site occupation restrictions locally on our lattice, or more globally to a finite carrying capacity. And that induces a non-equilibrium absorbing, active to absorbing phase transition for the predators. Generally, you would expect that to be in the directed percolation universality class. You can use this field theory to show that, not maybe rigorously, but certainly finely on a theoretical physics kind of viewpoint by mapping the field theory in this limit to what's called Regium field theory, which describes directed percolation. But if I want to change that and just tell you what the physics is that if we are near this extinction threshold, remember that means the prey have essentially taken over. So they're everywhere. So that predation reaction, which says A plus B goes to A plus A, really meant the predators have to meet a prey and then they can eat them. If the prey are everywhere, there's no constraint. So the predators will just be reproducing. And so instead of A plus B to something, you just get A to 2A. Because the prey are abundant. And then you have predator death, and you also have, that's a consequence of site restriction, you have 2A essentially going back to A. And so what you have is you have spreading particles, that coalesce and split. And that's the definition of directed percolation. The spreading direction is a special direction in space-time, we call it time. And then all you do is you're following this kind of emerging clusters of branching and coalescence. And if the system spans your entire length scale, then the system survives and is in an active state. If the cluster goes extinct somewhere, you're in the extinction state. And then indeed, at the critical point of that, you find the critical exponents of directed percolation. And those are the right critical exponents for this extinction universality class. And that's generically the case. So to check that, long ago I already looked at the survival probability number of active sites, which is the most efficient way to check these things, and we roughly find the two-dimensional directed percolation values. And then we did some more careful studies later that I go into next. But before we go there, I wanted to say that only a few years ago, Nigel Goldenfeld and his student Song Shi used this kind of mapping and directed percolation result to study the onset of shear turbulence in pipe flow. And actually they mapped this pipe flow shear turbulence problem to a predator-prey Lotka-Volterra model, and then inferred from there that the critical point should be directed percolation, and it works beautifully. So sometimes there are these really nice connections across different fields by intelligent mappings that are very fruitful. So there's one. Okay. So here we're looking at the extinction threshold. We're looking at the predator density at extinction threshold, which should be a power law. And you see, we barely get here at large times. And if you look, that's a log-log plot of the predator density versus time. If you look at the local slope here, so we just take local derivative and get what's called the locally effective exponent, at the critical line, which is roughly this red one, which is where you get the most rate slope, you see that we get barely after, 5 times 10 to the 10 Monte Carlo time steps, we get to this kind of stationary point, and we can extract the critical exponent. Likewise, we can check for critical slowing down, so look at these characteristics relaxation times, which we get from the Fourier transforms of these peaks, and measure the dynamic exponents and all that. And they do reasonably well with the dp universality class. But it's actually a lot more effective to look at what's called critical aging scaling. So this is non-stationary early time, much earlier time than stationary time scaling behavior that works for the system too. For that, you need to look at a 2-point correlation function at different times. If you're in a stationary regime, there should be a function of t minus s. And here is kind of this function shown as function of t minus s for various different times, and you see there is no collapse on t minus s. So we do get what's called aging. And what you in this case want to do is actually collapse the data not as a function of t minus s, but the ratio of these 2 times t and s that show up in this 2-time correlation function. That's an autocorrelation at the same position. And when you do that for sufficiently large times, both t and s, small times you don't get collapse, but for large times you do, which is kind of this purple line here. Then you can make them collapse with a wisely chosen exponent b, and you can also extract another critical exponent from the slope down here, which happen to be these predictions from the directed percolation field theory, and that kind of works nicer. And you get this already after 10,000 Monte Carlo steps. So also not cheap, but much easier to get to than the stationary regime. So that's just an advertisement for people. If you do critical behavior, looking into critical aging scaling is a very useful tool, and it does work in the system too, and allows us to really characterize this extinction threshold for this population. And of course, you might be able to use this as an early, but you're not really that early, warning indicator for population collapse. All right. Before I go now to further applications and variations, let me ask the audience again if there are any questions that I can help you with.
No questions so far.
No questions. All right. Then I'll just happily proceed. But once again, please do not hesitate to interrupt and just follow Reinhard's lead and jump in. So then now I'm just going to go through a couple of variations of these types of models that take us a little closer maybe to biological questions that you might interrogate the system with. Still all in kind of our toy model system, but in a regime where we have few enough parameters, few enough degrees of freedom that we can actually understand the fundamental mechanisms quite easily. So one that we've done lately is looking at now taking the carrying capacity, so the maximum number of prey that we allow, and make that a time-dependent function. Think, for example, of seasonal oscillations. The carrying capacity, in some sense, measures how much food is available for the prey, so how much population can the environment sustain. And so we just switch it periodically between some low value and some high value. Low value may be 1 or 2, high maybe somewhere between 5 and 10. And so here we might have the prey being very limited, which is really bad news for the predators, as we've seen before. Up here, the prey can expand, the predators will be very happy. So you essentially, with this external forcing of the carrying capacity, drive your oscillations. And you can then stabilize these damped oscillations to persistent periodic oscillations that keep going. So the seasonal external drive is really stabilizing these periodic response in the system and both populations, therefore. And that even works in a regime where, say, this is below the extinction threshold for the predators. This one is above. And if we just switch fast, which is almost always, we can let the predators who would otherwise go extinct be sufficiently stabilized by these periodic oscillations. So here's some examples of showing the typical asymptotic predator and prey densities as function now of the period or rate with which we switch. Now, obviously, if you do very fast switching, so this happens really quick on the time scale of these oscillations and spreading fronts that we were seeing, the system is just going to average over them. Now, since the carrying capacity turns out to be showing up as 1, inversely into the stationary densities, what essentially happens in this averaging is a harmonic mean over these two carrying capacities. And that turns out to be working as a really nice description what happens certainly for the prey. If you look at the scale, there's actually just a 10% difference here that at most the prey density does relative to this simple harmonic mean. So this is giving a largely quite good description. The predators behave slightly differently. There is deviations from there, which we do understand and which you can read in this preprint we currently have under review. And so that works nice. Because there's also a slow switching regime. If there's a lot of action going on before we switch, the system just does its thing, and then in a later period does its thing again, and essentially you just average these things. So the fast and slow switching regimes can be analyzed straightforwardly. Interesting things happen in between, and indeed there's some kind of resonance effect, as you would expect, right? This is an oscillating, damped system, and we drive it externally, so somewhere when the typical time scale of the internal system matches to the time scale of this external drive, you get some kind of resonant behavior, which we see both in the predators and prey. Positive for the predators, not so great for the prey. And the way that shows up in simulation plots or movies is that, if we tune the system down to where, say, only one set of activity front survives, it spreads, then we switch into this kind of high carrying capacity regime. System is very happy, spreads like crazy in both directions now, and then it gets suppressed again and switches again. So compared to what I showed you before, is we get kind of this periodic pumping of these activity waves that run through the system, which are quite cute, and in a deterministic low noise limit can get to more effects like period doubling and the like. That is familiar from nonlinear dynamics. So if you like, this is kind of a nonlinear dynamics application.
So there is a question again from
yes, very good.
So may I interrupt you again? If I look at the picture of the oscillations, I have the feeling there is a symmetry between A and B, in fact. They have the same oscillation frequency and so on. And
they have the same frequency, definitely, but the shape is not quite so symmetric. Right, let me just jump back like crazy here if I find this. You see, there is a bit of reflection symmetry in this kind of mean field description, and I think that's partially what you're seeing. But it is a nonlinear system, so it's not entirely symmetric.
Yeah. What makes so to say? Could you make it less symmetric and more symmetric so that you get? Oh, okay.
Yeah, just by changing some of these rates. But essentially what is always true is there's essentially a 90-degree or, pi/2 offset between the prey and predators. So that's very characteristic for this system.
So in some sense, one follows the other. So you have...
Yeah.
Okay. Thank you.
Yeah. But you see, especially down here, that's a little different. So up here in this high density regime, that's very true. Down here, the shape is different. Yeah. Good observation, of course. Any other questions? Okay, if not, then let's do something else, maybe also kind of physics motivated. This is a question, at least I could ask for the physical system as well. So forget the periodic drive now, go back to our original system that just oscillates by itself. But now we're choosing the predation rates, and that's really the only interesting bit because these are the nonlinear processes that we're talking about. We're choosing the predation rates to be randomly distributed in our spatial system. So we make them a quenched random variable in physics parlor, and each site, for simplicity, has a different rate. These are probabilities per unit time, so I need to keep the probabilities somewhere between 0 and 1. So I cannot do Gaussians, but we can do truncated Gaussians and normalize those. And then just run the system. So, each space point has a different predation rate, and whenever particles encounter each other on these space points, they will be subject to these rates. Now here's a comparison when we look at, say, the predator density, and actually prey density would look pretty much identical, as a function now of the width of this distribution. So if this is very narrow or actually zero width, then we have a pure non-disordered system, and that is kind of the track you see in the lowest curve here. And then if you increase this randomness by increasing this width, we see the predator density goes up. And now what surprised us is that is actually true for both populations. Both asymptotic densities go up. Now, not hugely, right? This is only a 25% effect, if you like, from density near 1 to density near 1.25. But, 25% effect in ecology is actually quite noticeable. The other thing you observe is that the initial oscillations become bigger, and you also observe that the relaxation to the stationary state is actually faster. That's a little hard to see in these tracks, but you can extract that from the Fourier transforms. That's not surprising. In a disordered system, you get enhanced damping, and so relaxation to the stationary state is faster. Now, what explains the fact that we actually have for both populations this kind of environmental variability or quenched randomness is beneficial is ultimately that if you look at these correlation lengths of the both predator-predator or predator-prey cross correlations, you find that the correlation lengths decrease. So each of these kind of local oscillating clusters that spawns of these activity waves becomes more localized, more dense, and that means you can fit more of these into a finite system. And if you can fit more of these into a finite system, you actually increase the net density. And so that's how we think this effect comes about. So it is a correlation effect ultimately, and quite cute, but it means that environmental variability is really enhancing both the hunted population and the predator population. All right, you can now ask an entirely different question that you cannot do in chemistry, but you can do in population dynamics. In the previous part, we assigned different rates to each space point. But of course, you can just say maybe each of my individual particles is more effective in hunting or more effective in evading a predator. So we now attach different rates to individuals. So we call them predation or evasion efficacy for the predators and prey, respectively. And then you have to make a decision. When they meet, what is the effect on the net predation rate? And what we said is, well, we just take these rates attached to our individual particles, and we just take the mean of that and call that the predation rate. We can argue if that's useful or not, but that's the simplest choice. So you might have a very effective predator in evading things, meeting in hunting things, meeting in a prey that's very effective in evading a predator. So this would be a large number, this would be a small number, and they would add up to some effective predation rate. Now that's all fine, but then you can, that setup now allows you to do some more fun things that are also not possible in chemistry and physics, but in biology. Namely, you can have the offspring particles to inherit the rates from their ancestors. So for example, we can say that, whenever we take prey reproduction or the predation reaction, which effectively leads to predator reproduction, and we take the offspring particle to be inheriting the efficacy from their parent, but maybe with some error. So we choose a Gaussian truncated, centered at the rate of their parent, but with some characteristic width that allows for some kind of mutation variance, if you like. And then you can run the system, and you run spatial organization, but you also will dynamically change the probabilities or the distributions of these assigned efficacy rates, both for the predators and prey, so you get some evolutionary optimization. So I'm hoping I made the model clear. So we have some variance of this mutation, and of course we also have some variance of the initial setup, but the more important one is this mutation variance, and we can now check for the final distribution subject to these nonlinear predation processes in our system. And so here's some example results. This is for some really tiny mutation probability widths, and shows you the asymptotic distributions for the predators. Oops, this is up here in blue now. We changed our color coding for this one, I apologize. And the prey down here. So the predators, of course, evolved to a large mean predation rate. The prey to a small mean predation rate. And the same is true when I make these widths larger, just the final widths are also larger. And so that is what we're seeing here. Yeah. And it turns out that this happens really fast. So there's really two timescales, a very fast timescale, in this life of generations, where the probabilities distribution of these rates optimizes themselves, and after that the system just is essentially stationary. So this happens within something like 100 Monte Carlo steps or so, and for the next 10,000 nothing happens anymore. But notice, because this was a nonlinear process, we do not get fixation. So it's opposed to what's called genetic drift, or genetic really drift and diffusion, as it should be called, very similar to processes that Nir just showed us before. In a linear process with drift and diffusion, you would end up at either of these borders at some kind of absorbing state, and the system would just be, full predation rate 1 for the predators and predation rate 0 for the prey. Not possible here, because this was an underlying nonlinear process, so there's a finite width always, and we do not get fixation. They always have these distributions. We did some kind of mean field theory for this too, which works the following way. You just take these, individual rates and just spin these different populations, if you like, as quasi-species that are described by these effective rates, and then write down mean field Lotka-Volterra rate equation for, however many quasi-species you like, and then solve that numerically with the mean field factorization, and that's the dotted lines here. Now you see that works quite nicely in the center. That's when you actually don't have very large correlations, and is off near the boundaries when you do have correlations. And non-mean field effects are important. And then there's one funny limit, which is uniform distributions initially. You can solve the asymptotic distribution exactly. That's doable, fairly straightforward. Actually, the predators stay flat. The prey take this 1/8 asymptotic distribution, which is the kind of limiting distribution for these wide ones here. So the message here is fast optimization, and then the system remains stationary. So that allows us now to do one more thing, which is asking the question of, nature versus nurture. What is winning if I combine spatial variability, so how things fluctuate in space with respect to this predation rate, with demographic variability, this kind of inheritance with noise effect. And so the way we did this, we allowed both spatial and this, variability attached to individuals, and we just give that a relative weight. Again, for simplicity, we just take an average. So we take this kind of, interpolation parameter zeta, that if it is 0, we're just back to this, purely demographic variability. If zeta is 1, we have this kind of purely spatial quenched noise. And then we run combinations and see, what happens to the asymptotic densities, which are again very parallel for both the predators and prey. So here's this graph. This is at zeta being 1 to the left, which means we have pure spatial variability. And see, we do get our 25% effect that I was showing on the previous U graph. So quite some drastic increase in the asymptotic, if you like, fitness for both populations if I have these spatial variations. If I have purely demographic variability, so spatially uniform, but the individuals can change, you get a 10% effect, which is this border. And in between, you have this kind of interpolation. So interestingly, spatial environmental distributions, this kind of spatial variability is more important, has more effect on this model in the long time limit than these kind of demographic variabilities have. It is crucial for both populations to optimize, otherwise they would go extinct very quickly, so they have to do this. But once they've done it, the effect is almost neutral, right? The predators optimize, the prey optimize, both of them win a little bit by maybe 10% relative to without this variability, but not much more. The quenched spatial effect is actually bigger. All right, so this is all I wanted to say about these kind of two species predator-prey models, and I see I have about 5 minutes or so maybe left, which is fine, to talk about extensions to more species. But again, before I do that, let me see if there are more questions.
So if you have some question, raise your hand or just ask directly or write in the chat. I don't. And you
Okay,
have.
then I'll just
Okay.
continue and we'll have more questions at the end.
I would ask a question here at this point.
Go ahead.
You have you spoke about the system with two species, A and B.
Correct.
And you compared with computer simulations, theoretical aspects. Now my question would be, are there any systems of bacteria or something like that where you find all these effects? So to say,
Yes.
the Drosophila for this equation.
Yes. So I would like to see more of them, but there are a few which are promising. Some are a bit dated. So one is you can actually do your Drosophila thing. You can put some parasites on fruit flies, and then the parasites are like the predators, and the fruit flies are the other things. But the fruit flies sadly fly, right? And so that means the system is well mixed if you investigate that. And if you do this in a nice container, have your fruit flies in there and the parasites, and the fruit flies move around like crazy and mix, you do get the well-mixed original Lotka-Volterra mean field description that works really nicely. So there's an experiment, but sadly not at all what I'd like to see, which is looking for spatial correlation and fluctuation effects. So the next thing you can do is indeed bacteria. But then people typically do them in a petri dish, and then maybe move them to another petri dish. And so these are not really quite spatial systems. These are like zero-dimensional systems, and you can look for the temporal fluctuations, but not really spatial. Then there's another thing you can play with, which is you can actually program DNA, different strands to behave like predators and prey, which is very beautiful. It was done near Paris maybe about 10 years ago. And then you see these fronts. So that's a regime where you actually see these, activity fronts of the predator DNA hunting the prey DNA. But beyond that, very interesting. But beyond that, people haven't actually analyzed that quantitatively a lot. And these fronts are definitely in a fast diffusion regime. Now, if you're in a fast diffusion regime, sadly, you're again suppressing the fluctuations. And so this is like a mean field reaction diffusion regime, right? So factorization is fine. You see nice, smooth spreading fronts, but you don't really see the fluctuation corrections. Now, I think that's in principle accessible to that. It just means you have to tune other parameters, but hasn't been done yet as far as I know. So I'd love to see more of these, and I think it's in principle accessible, but if I had data, I would show them. I can assure you of that. So great question. Thank you, Reinhard.
Thank you.
Okay, thank you. One more question from Yuri Holod.
Yeah, thank you. And if we go beyond the realm of biology and even of chemistry, say economy, maybe something else, would it be tractable within similar models? Probably you were thinking
I think so.
about
Yes,
this.
absolutely. Right. This is just competition. This doesn't have to be predation. As I said, I'm just using the language of ecology, but really doesn't need to be. So yes, and also just before I get to the three species systems, if you go back to our original reaction here, right, this A plus B to something, that's just an infection system. This is an infective agent that infects a susceptible person. So this is a very key ingredient of the SIR model for spreading epidemics. Because then there follows something else that makes differences, but the nonlinear effect is the same. So I think that's a very generic scenario to look at, and will have a lot of applications also. I think in principle in, as you said, economics, sociology, and the like. Yes. So I view this as a paradigmatic model. One of the main Ising models in out of equilibrium systems that we should understand, and then once we've understood it, we can use that fundamental understanding to apply that further in more complex scenarios.
Thank you.
Well, if there are no more questions, then in this very realm, let me go through this, if I've toggled it right, three species system. And you can do more, as my colleague Michelle Pleining at Virginia Tech has done, but let me just focus on this one. So that's just a cyclic extension. So cyclic competition, which actually is quite an important system to look at in game theory and decision making, for example. But let me not go into this. So this is like cyclic Lotka-Volterra processes. A it's B, B it's C, C it's A. And so, akin to the game we all played, or still play maybe sometimes with our children or grandchildren, this is like a rock, paper, scissors model. And you can give them equal rates or not, as you like. Okay, so this is the classical cyclic Lotka-Volterra rock, paper, scissors model. And here we have total particle number conservation. So all we do is, there's no separate processes aside from this, is, B gets replaced by A here, C gets replaced by B here, A gets replaced by C in the third process. So the total particle number is strictly conserved, not just on the mean field level, but on a fundamental stochastic process level. And if you look at the corresponding spatio-temporal system at long times, it's clusters. No spreading activity fronts, nothing really terribly interesting, just fluctuating clusters. Some of those might go away, be replaced by others, but it just keeps going, but it's just clusters. Another variant of that model that was written down by May and Leonard in the early 70s is here, where you essentially split up this predation reaction. So you do A eats B, and independently A produces offspring. And likewise, cyclically for the other two species. If you do that and you look at the spatial system, you find spirals. The system spontaneously generates, these moving spirals. These are not static. They keep moving and rotating, as I'll show you in a second. And, of course, in a continuum limit, you could view these spirals as emerging topological defects in the field theory associated with that. And, they're equally likely in different orientations, can annihilate all these kind of fun things. The way they're generated is just kind of by a local excess. So if I have this kind of local, if I go, say, clockwise, I get red, green, blue here, red, green, blue. And so that will form the spirals going one way, depending on who eats what. Red eats blue, blue eats green, and what have you. If in another corner if I go clockwise, instead of red, green, blue, I have the other chirality red, blue, green, then I would just set the spiral up in a different setting. So it's just kind of local density excesses that determine the orientation of these spiral arms, and they can annihilate all kinds of things. This one, of course, does not have particle number conservation. It runs to a stationary state where the densities might all be equal and stationary, but you do not have particle number conservation on an individual stochastic process level. And that really makes the difference. So over here, we have an overall diffusive mode, which is the total particle number. And if I have this overall diffusive mode, it can actually transport particles across, these maybe trying to emerge spiral arms, transport them over very quickly, and that destroys the spiral arms. Another way of seeing that this particle number conservation kills the structures is, here I do need to have, by total number conservation, if I have kind of positive oscillations for the red species, somewhere the blue and green need to go down in the vicinity to keep the total particle number fixed. And so I can never have coherent oscillations of all species locally too close. And so the conservation law actually kills these spontaneously emerging structures. So that's just a preamble for the following thing that we did also quite lately, and it's the last thing I'm going to show you, which is combination of such systems. So now I'm taking, say, one RPS, cyclic Lotka-Volterra model, combined with the May-Leonard model. And of course, we do that still on a torus. So we have a slab that's RPS, and then we have a larger bit of our torus, the two-dimensional lattice folded onto each other, which is subject to the May-Leonard rules. And so what that means is, if I have my particles that can move around through diffusion or just being generated by offspring production, if they cross the boundary, they're just immediately subject to the other game rules. So in the red area, they're subject to rock, paper, scissors rules. In the green area, they're subject to May-Leonard rules and have an interface. And if I run this is what happens. So I get these kind of clusters in the thin rock, paper, scissors slab. I get spirals in the May-Leonard slab. And in between, we have these emanating kind of almost plane waves that come from the rock, paper, scissors into the May-Leonard system. Now, the origin of those is that the stationary densities are different in both cases. So there's a density gradient that sets up a diffusive flux on both borders. On this again. But that's it. The bulk is just May-Leonard, the bulk is just rock, paper, scissors, and then we have some characteristic boundary effects. Okay, so that's what you would expect, I think, generally by gluing these such systems together inhomogeneously. Well, we thought, so let's do something else. Let's look at these May-Leonard models, one which is very symmetric and one which is very asymmetric. So we have one of these species that's very much more effective or less effective in devouring their prey, and the other ones are equal. In the lattice system, if you make the asymmetry large, the system becomes actually quite unstable. In a finite system, it's very close to one of these extinction points. Extinction points meaning, one of these species dies, their predators will die, and then the only thing that will survive is the third species. So you get two species extinction. So this is set up such that we have a stable, symmetric May-Leonard model here, and an unstable, very, very prone to extinction ecology on the right-hand side, which is much bigger. So we still have this kind of diffusive flux across. And let me just run this one to show you what happens. I'll run it twice, I'll let it just run first. And so you see, ultimately, what we're seeing is that the unstable system becomes stabilized by this diffusive coupling to the symmetric variant. And so let me just stop this here quickly. So what is happening is, in this unstable part, the blue species has just kind of almost disappeared here. Green species has eaten it, the red is now eating into the green. And then as we go a little further, you see that the green has disappeared, and really in the bulk of this unstable ecology, we have two species extinction. In this case, it happens only the red ones are left. But now from the stable region, we get these kind of emanating plane wave fronts that eat into it. And then at some point, they're just going to merge and interact and set up, and that's really largely independent of the system size here, set up these spirals that keep the system going. So we can actually stabilize this vulnerable ecology through invasion from the boundaries from a stable system. All right, with this, I think I've talked amply enough. I just have my, apologize for that very dense summary and conclusion slide, which really just tells you these are fun models to play with. There's a lot of variants you can pick, some of which are physics motivated, some of which are biology motivated. And we'd love, following up on the questions I just had, we'd love to see actual experiments testing some of these. I think that should be producible for both 2 and 3 species models by synthetic biology. Other models that are like that, we actually had that, and we had some fun in modeling those. But it would be nice to see these. But I think it's just a really nice playground for physicists to be active in. And so, thank you very much.
Okay, thank you very much. So we have time for questions. So we had some questions during the talk. So you can raise your JK. I don't know who is it. Please proceed with the question.
Still muted, I think. You may need to unmute your microphone.
JK, I don't know who is it. You should unmute yourself. Or please send the message in the chat. Yuri Kozitsky, yes, please unmute the microphone, to ask the question.
Do you mean me?
Yes.
Can you hear me? Can you hear me? Can you hear me?
Yuri Kozitsky, we see you and we hear you.
Yes, yes. Yuri Kozitsky. You are muted. You should unmute the microphone. Click. Okay, I'm sorry. Yuri Sikorsky, please proceed maybe with your question and...
Can you hear me?
Yes, we hear you.
Yeah, okay. First of all, thank you for a very exciting and inspiring talk. It was really very, very interesting. You have pointed already out that the theory and the Lotka-Volterra application is applicable for chemical reaction, for example, in catalysis.
Yep.
Yeah, Gerhard even has such a fall in this Nobel Prize talk showing lynxes and rabbits. And there is also some feedback. The problems which appear there can be, of course, also discussed in your application for the real prey and predators. And my question is, the space where the predators and prey interact in your theory is homogeneous. The probability does not depend from the location where the prey and predators interact. However, in real life, this is not the case. There are mountains, there are forests, different places where the probability of success during the hunting is, of course, not the same. And my question is, can this be considered in any way in your theory, in your calculations? I mean, special in homogeneity.
Yeah, so yes, about 3 times. First of all, it was actually, I forget which one of the gentlemen, either Lotka or Volterra, actually derived that model not for ecology. One of them did for the fish population in the Adriatic Sea.
It was Volterra.
The other one was for chemistry. Yes.
Yeah, it was Volterra.
Right, and the other story is, as I said, people immediately, or at least 20 years later, started to criticize the model because it's artificial and has these artifacts. And to actually get stable oscillations, people would put in the delays into the mean field model, and then you actually get a robust system. What we are saying is, not disputing that, what we are saying is it's also true that if you take the model away from the mean field, you do get really stabilized oscillations that are stochastic, that are very robust. And I didn't get to tell this, you can actually modify the model quite drastically and still get these oscillations. Now, your second part of the question, the first is probably more comment, is can we do spatial variations? Absolutely. And so we did the spatial randomness. We did a complete random distribution on predator efficiency. And yes, you can do it. And of course, you could do kind of more patches. We also did one variant where we had half of the space is large lambda, half of the space is small lambda, half of the space is in the extinction regime, half of it is elsewhere. So you can do that all straightforwardly in this. And I would love to do more, but especially if I had an experimental system directly to compare with a model, because otherwise it's a bit arbitrary to what to look at. But absolutely, it's in the simulations, it's a very straightforward means to implement that. And indeed, for these species models, I showed you some variants also where we have the spatial inhomogeneity. So yes, you can do it. And if I had good motivations, I'd put a student on it immediately.
I have a good motivation. And the question is, are you interested to apply your theory to surface system, to surface reaction, like hydrogen oxidation?
Okay, we should definitely talk more, Yuri.
I will write you.
Good, thank you.
Thank you very much. Vielen Dank für schöne Erklärung.
You're most welcome.
Okay, please. The next question.
May I now ask? There was a problem with my communication here.
Now we can hear you.
Can I ask now?
Yes, please. We can hear you.
Thanks a lot for the so impressive talk. It was full of information. And so maybe I lost this. So you mentioned 2 more models, May Leonard and RPS model.
Right.
So as generalizations of the Lotka-Volterra, could you show the corresponding differential equations?
I could. I don't have them on my slides, but they're also fairly straightforward. So I may try to do this by hand, going back to the Lotka-Volterra differential equations. which are...
What should be changed?
So these terms go away. So there's no mu A, no sigma B, because, So for the first one, you would just have lambda AB. That's A eats B, but then you would have a minus lambda AC, because the A's get eaten by the C, and you do that cyclically. That's the cyclical Lotka-Volterra. For the male Leonard, it's a bit more complicated. You would have that too. So we'd have these processes for the predation, and then you would have the spontaneous offspring production. So for example, here the B gets eaten by the A's, that would stay. And then you would have another, which is sigma times B squared. No, just sigma B. So which should look like that and cyclic through. So essentially that's how it looks. And we published that too. And you can do the full field theory. You can do the full stochastic field theory in these cases and analyze those as well. Yeah.
And then one more question. Do you know individual-based models corresponding to the models which you mentioned in your talk?
What we did simulate are the individual-based models. Right? We did not simulate the differential equations.
No. It's it depends on what do you mean in differential equations. I mean that each individual is attached to its own, each ascribed by its own traits like position and so on.
Right.
And then they compete like something which is behind your simulations.
Well, this I would think is a very rough model for actual ecological species, right? So some animals, individuals are more efficient predators, and some animals are more effective in evading their predators. And of course, that's a lot more complicated than just saying this is one overall rate. This is a very strong physics, spherical cow-like approximation we're doing, but that's trying to capture these individual traits in population. Even in bacteria, you have that. Some bacteria, when they compete, they do this by actually excreting toxins that hinder or even kill the others. And some just have a higher output of concentration of toxins than others. And that variability is we try to capture with this kind of one individual dependent rate that we looked at. But it's a very coarse-grained, effective description, absolutely.
Thank you very much.
You're most welcome. Thank you for your questions.
Okay, and then the question or comment from Yuri Holovich.
Yeah, thank you. Thank you very much for your talk. And the question is again about inhomogeneities. You were introducing random reaction rates, and especially thinking about possible applications beyond biology and maybe chemistry, say economy. Some agents are inhomogeneous not because, so to say, they have different reaction rates, but they have more access to different other prey or to different other predators. It would look as if you do your simulations not, say, on torus with lattice structure, but on the network, on graph.
Absolutely.
Do you plan some activities in that direction, or maybe you're doing something in this direction?
Well, we did for COVID spreading. So if you do epidemics, you definitely want to do this on interaction networks, and there we did that. For the predator, for this type models, predator prey systems, we haven't. I think some other people have. Once again, if I had some actual model with real data, I would find it a very interesting avenue to proceed into. I'm always a little this is following up on Reinhard Volk's question earlier. I mean, it would be nice to have actual data like NeoGov had to direct us a bit more in what model variants to look at.
Yeah.
So if I had an experimental system that would actually say, this is what we should be doing, then we can easily modify, somewhat easily modify our algorithms and do it. But without having that motivation, I'm looking kind of for more fundamental questions to answer at this point.
I see, yeah.
But you're absolutely correct, Yuri, of course, for applications to economy, this is not on a two-dimensional square lattice. You have to worry about connection networks and who talks to whom with a realistic architecture.
Yeah. Thank you. If I may, another question. In fact, the question appeared, so to say, maybe 1 first quarter of your talk. You mentioned that you noticed some real conservation laws which have physics behind, and there are some fake conservation laws, and that can be done rigorously, or that's more the art of the researcher. So if I would be the newcomer and I see that something is conserved and I have not good feeling whether it comes from physics, I would only wait, say, continuing simulations, and then I see, the conservation doesn't hold anymore. That's the way people do, or you have some other criteria to discriminate between?
I would say, Yuri, as we all know, right, this is the art of theoretical physics. Some conservation laws are obvious, like the one for the total particle number. That's hard to miss. Some are less obvious. And in this business, I haven't really seen many of those, but there can be hidden conservation laws. And if they're there, they're very important. But then it's not obvious to find them. And what happens often is that you either do simulations and you notice something funny, and then you realize something else is going on. So it's this nonlinear feedback that enhances your understanding. So no general rule for that. But what I wanted to warn about is, don't believe mean field rules generally. For example, if I look at the RPS system also, there is on the mean field level, there is, if you write down this is going too far, sorry. If you write down the mean field equations that we just discussed in the earlier question, for this system, you find that the product of A, B, C is also conserved. That's complete nonsense on the stochastic level. That only happens on this level of the mean field rate equations with the factorization. And so those you need to be careful. You can get mathematically conserved quantities in an approximation. That's not likely to capture a lot of physics. It can get you some approximate physics sometimes, but not actually. While the real conservation laws provide really hard constraints. And if I had a general rule to always identify them, I would share that with you, Yuri, and we both book a ticket to Stockholm, right?
Thank you.
Okay.
Yes,
Following
please.
this discussion, I had another idea. I mean, couldn't you apply these equations to social systems like political parties? I mean, we have over the time we can look at such systems, how they change, how they make coalitions or something like that. That would be another application, I think.
Definitely, and there are people doing such things, of course. Yes,
I can imagine. Yes, maybe there are already.
Absolutely. So that's what I was really trying to say, that this is just one of these paradigmatic toy models that with the proper modifications is very broadly usable in all types of different contexts, which really I believe is the beauty of statistical physics, right? Like with the Ising model, that by itself maybe doesn't describe anything real, but when you attach it with the right wrinkles, it's a very powerful tool and can be applied to anything between magnetism and neuroscience and beyond. And likewise, there's a few more of these models, such as directed percolation, predator-prey systems. As I was saying, it also describes the onset of turbulence in certain pipe flows and the like. And I think we just really need to keep understanding these fundamental basic building blocks that would then allow us to go and branch out to other systems. But absolutely.
Yes.
As you know, there are these motor models which are different, that people use a lot in opinion dynamics and the like, and I'm sure there's lots of these variants we could play. Absolutely.
Yeah, thank you.
Okay, some more questions do we have? Okay, it was nice talks, and I see a long discussion. So thank you very much for your talk, and thank you all people who attend the workshop and all the lecturers from the previous days and co-chair people. So thank you. It was nice 3 days, and I hope the next year we can meet in live. And that is the end of this session.